second session of the day. The first speaker of the second session is Peter Trifonov, who is at the ITMO University in Russia. We had several pre-coded polar code talks yesterday, very interesting ones. I think Peter Trifonov was one of the earliest people to talk about pre-coded polar codes, if not the person who introduced pre-coded polar codes. So we're really excited to have Peter give a talk here. Peter, please take it away.
Thank you very much for inviting me to this wonderful workshop. What I would like to present today is a novel construction of polarization kernels, which allows one to obtain polar codes with quite low scaling exponent and reasonable decoding complexity. Well, I think everybody knows what is polar code. It is, but I would like to discuss today not just conventional Arikan polar codes, but polar codes with large kernels. Such codes are based on a square invertible matrix K, which is called polarization kernel. If it is not permutation equivalent to an upper triangular matrix, then it induces a number of bit subchannels with such probability transition functions, and the capacities of these bit subchannels converge either to 0 or 1. The encoding scheme for such generic polar codes looks like this one. It is somewhat similar to the encoding scheme for Arikan polar codes. One can still decode polar codes with large kernels with the successive cancellation decoding algorithm. And the complexity of this algorithm is still n log n. But it is not so easy in practice, and I will discuss it in more details a bit later. Recently, a number of papers were published which show that essentially there exist polar codes with large kernels such that their scaling exponent converges to the optimal value of 2 with the kernel size growing to infinity. And there exists a specific polarization kernel of size 64, which has scaling exponent approximately equal to 2.87, which is already less than the heuristic estimate for the scaling exponent of specially coupled DPC codes. So it seems that one can easily achieve scaling exponent better than LDPC codes. But in practice, things are not so good. The problem is how do you implement the computation of probabilities which arise in the successive cancellation decoder? One can implement decoding either in probability domain or in the domain of log likelihood ratios or even approximate log likelihood ratios. Such approximation results in negligible performance loss. And the question is how to compute these log likelihood ratios. This problem reduces to maximum likelihood decoding of some linear block codes generated by polarization kernels. If you try to implement such computation in a straightforward way, then you would obtain either summation or maximization of an exponentially large set, and this results that the successive cancellation decoding complexity grows exponentially with the size of the polarization kernel L. And if you consider, for example, polarization kernel of size 64, then this obviously becomes completely unimplementable. But fortunately, this complexity can be reduced quite substantially by employing well-established low complexity maximum likelihood decoding algorithms for linear block codes. Now I'm going to briefly review the algorithm introduced in this paper. It is actually based on the recursive maximum likelihood decoding method introduced in 1998 by Fujiwara, Yamamoto, Kasami, and Lin. And the idea of this approach, I mean the approach for maximum likelihood decoding of a linear block code, is as follows. Given received noisy vector, we recursively partition it into a number of small sections. Then find for each section a few most probable vectors corresponding to the corresponding piece of the received vector, and then recursively combine these vectors into longer ones until we obtain the most likely code word of the considered linear block code. This approach extends naturally to the problem of kernel processing, and in this context, it admits several other simplifications. For now, I would like just to briefly describe what exactly this algorithm computes. It operates as follows. Given some linear block code, for example, the code generated by kernel rows starting from I down to the bottom row, we need to introduce a punctured code for each section, and we need to introduce a shortened code for each section. We need to compute such expression where T are so-called composite branch tables. They contain the correlations for the most likely representatives of the cosets of the punctured code with respect to the shortened code. The complexity of this computation grows exponentially with the dimension of the punctured code. Actually, it is not really important what does this expression means. The key problem is that the complexity grows exponentially with the dimension of the punctured code. And if we need to obtain low complexity kernel processing, then we should try to construct polarization kernels which have as small as possible dimensions of such punctured codes. And of course, this has to be done subject to constraints on polarization rate. So what is polarization rate? Each kernel can be characterized by so-called partial distance profile. It is the minimum Hamming distance between the ith row of the polarization kernel and the linear space generated by bottom rows. And the rate of polarization can be computed in this expression, and it essentially shows how good are polarization, how good are bit subchannels induced by polarizing transformation based on kernel K. And the successive cancellation decoding error probability for appropriately constructed polar code is given by this expression where beta is an arbitrary value less than E. So to obtain a good polarization kernel, we should try to keep these partial distances as high as possible. But on the other hand, there are some fundamental limitations which relate partial distances and dimensions of these punctured codes. So if you try to increase partial distances, then most likely you will have to increase the processing complexity. Fortunately, there is a very nice code construction which allows one to obtain codes with a sufficiently high minimum distance and still low trellis complexity, which actually is also important for the considered recursive maximum likelihood decoding algorithm. So now I'd like to briefly recall what are generalized concatenated codes. Such codes rely on a family of nested inner codes, which are generated by some matrix B. Also, we need some outer codes defined over some extended fields, and these extension degrees must be related to the dimensions of the inner code in this way. And if we can combine these inner and outer codes to obtain a code with such parameters. The encoding procedure is as follows. First of all, we need to encode the data with outer codes and store the obtained code words as rows in a table. Then we need to expand each symbol of code words of outer codes to obtain a column vector of length mi. And then we need to encode each column of the table with the 0th inner code. And if you now read the obtained table row-wise, then we obtain a code word for generalized concatenated code. And what we propose to do is to use the construction of generalized concatenated codes to obtain polarization kernels with sufficiently good polarization rate and reasonable processing complexity. So let us consider, let us try to combine a few small kernels into a large one. We will need some outer polarization kernels, which are invertible matrices over some extended fields. We also need an inner kernel, which is also an invertible matrix with some partial distance profile. And how do we combine such matrices? Let us partition K into a number of row types of size mi. Let us consider some basis of the extended Galois field. And let us multiply the elements of this basis by rows of the corresponding outer kernels. And let us further expand the obtained values in the corresponding basis. And so we obtain such values v with this very long index. Let us now pack these vectors, this coefficient into a long vector. And let us further multiply the obtained vectors by the corresponding elements, by the corresponding submatrices of the inner polarization kernel. So Ki is the ith stripe of the inner polarization kernel, which corresponds to the ith outer code, similarly to the construction of generalized concatenated codes. Let us consider an example. So let us use this matrix as inner kernel as well as 0th and 2nd outer kernel. So we partition it into 3 stripes. And for this middle stripe, we are going to use an outer kernel K1, which is defined to Galois field 4. It is actually a Reed-Solomon, an extended Reed-Solomon kernel. And if we do the row expansion, as I have described it on the previous slide, then we obtain 2 such vectors. And the expansion for the top and bottom rows corresponds actually to a straightforward Kronecker product of matrices. It is possible to show that the obtained polarization kernel has partial distance profile, which can be derived from partial distance profiles of the component polarization kernels. Let us consider some specific examples. We are going to use as an inner kernel a so-called permuted Arikan kernel, which is obtained by sorting rows of this Arikan matrix according to their weight. We also need Reed-Solomon kernels of the size which is related to the weights of to a number of distinct weights, to the number of rows of each particular weight you can obtain from this construction. For example, let us consider permuted Arikan kernel of size 8. So here we have one row of weight 1, one row of weight 8, and 3 rows of weight 2, and 3 rows of weight 4. So we need 2 outer kernels defined to Galois field 2 to be used for the top and bottom rows, and also 2 instances of outer kernel defined to Galois field 3. And here you can see such such kernel, it is again a Reed-Solomon kernel or Galois field 2 to the power of 3. Another example is based on this handcrafted kernel. This is actually a kernel of size 16, which was obtained by Grigory Trofimuk, and it has very low, quite low scaling exponent, and also very low processing complexity. We can combine it with our Reed-Solomon kernel of size 4, and I will show you a bit later what parameters you can obtain with this construction. But before proceeding into numeric details, I would like also to introduce some tweaks which can be used to either to reduce the processing complexity or to slightly improve scaling exponent. The first trick is to permute rows to ensure that all weight 2 rows and weight L/2 rows occupy positions either at the top of the matrix or at the bottom of the obtained matrix. This helps one to substantially improve the scaling exponent. Another tweak is to use shortening of polarization kernels. This essentially corresponds to employing outer kernels based on shortened Reed-Solomon codes. And here are the parameters which you can obtain in this way. Here, K64 corresponds to a straightforward application of the proposed construction based on the permuted Arikan kernel and Reed-Solomon kernel. We can see that it results in scaling exponent 3.13. If we permute weight 2 rows in the obtained kernels, then you get scaling exponent slightly less. And the processing complexity under the recursive kernel processing algorithm is approximately 10 to the power of 5. And such a permutation slightly increases it. Is this value small or big? We need to compare it with the state-of-the-art kernels. I have, to the best of my knowledge, there are two published kernels of size 64. One is extended BCH kernel, and another kernel was published by Yao, Fazili, and Verde. And the processing complexity of these kernels is really huge. And so the obtained kernel has several orders of magnitude less processing complexity compared to these kernels. If we use a construction based on a handcrafted kernel, then we obtain polarization kernel with slightly lower polarization rate, slightly higher scaling exponent, but its processing complexity becomes even less. Here, the processing complexity is reported in terms of the number of summation and comparison operations. If we apply row permutation to this kernel, then scaling exponent becomes somewhat less, and the processing complexity increases approximately by a factor of 2. But it still is much less compared to this value. It is possible to apply shortening to the obtained polarization kernels. And here you can see a list of parameters for a number of such kernels. And you can still see that the processing complexity of these kernels is still quite small, but it still grows exponentially with the kernel size. Here you can see the performance of polar subcodes of length 4000 and rate of 1 or 2 based on these kernels. The magenta curve corresponds to the code based on the Arikan kernel, and these colored curves correspond to the obtained kernels of size 64, and the black curve corresponds to the code based on a kernel of size 16. Here the results are reported in terms of frame error rate obtained with the least successive cancellation decoder at signal-to-noise ratio 1.25 dB. These results are reported in two ways. The left plot shows here least size in the least successive cancellation decoder, and the right plot shows the number of summation and comparison operations. As it may be expected, the best performance for a fixed list size is obtained by the codes with based on the kernel with the smallest scaling exponent. But if we plot the same results in terms of actual number of summation and comparison operations, then here it appears that the code based on a handcrafted kernel of size 16 provides the best performance and complexity trade-off. And the code based on the kernel of K64T shows second is somewhere here. And anyway, here we get better performance complexity trade-off compared to the code based on Recon kernel. I would like to emphasize that here there was no effort to derive a kernel-specific kernel processing algorithm for Red kernel. Why for the processing algorithm was explicitly optimized for the case of the kernel of size 16. So actually, I believe that there is still a lot of space for further complexity reduction of the for this red curve. Here you can see some other simulation results for polar subcodes based on various polarization kernels. So these yellow curves correspond to classical polar code based on a kernel of size 64. And the remaining curves correspond to polar subcodes based and also plain polar codes based on the proposed kernels of size 64. And here again we obtain the best performance for the codes based on the kernels with the smallest scaling exponent. And I would like to emphasize that although the BCH kernel of size 64 seems to have even better scaling exponent, here we consider just plain polar codes based on BCH kernel, so they still have somewhat inferior performance compared to polar subcodes based on these improved polarization kernels. Just to clarify, polar subcode is just another term for pre-coded polar code. Here you can see a comparison with 5G LDPC codes and polar codes based on the polarization weight construction. And here you can again see that polar codes based on a kernel of size 64 provides quite substantial performance gain compared to the 5G LDPC code. And this gain is obtained already with a list size 4. So it is it seems to be easy for implementation. So to conclude my talk, I would like to emphasize that the construction based on generalized code concatenation results in polarization kernels with quite small scaling exponent and reasonable processing complexity. And I believe that this processing complexity can be further reduced. And polar subcodes based on generalized concatenated kernels can provide both performance and complexity improvement with respect to the codes based on Recon kernel, and also such codes do outperform 5G LDPC codes. So that's all for my talk. Any questions?
So we have time for a couple of questions. Yeah.
Nice talk. Thank you, Peter. Can you explain the A parameter in the second to last slides?
Here it is a number of type A dynamic frozen symbols. So actually, this is just a specific parameter of the construction of polar subcodes. This is here impose a number of parity check constraints on some input symbols of the polarizing transformation. So it essentially provides some trade-off between performance and list size needed by the decoder to obtain near maximum likelihood decoding. Actually, quite similar results may be obtained by using some kind of CRC.
So very nice talk. Thank you. I'm curious. I think it's very nice to have beaten the performance of the 5G LDPC. If you do the full computation of complexity, probably still the 5G LDPC wins in complexity, I'm guessing. But do you think there is an opportunity still to bring the complexity down for the polar case?
Well, actually, I'm not so sure about the statement that LTPC beats in terms of complexity. Actually, if you make a good implementation of least successive or even the decoder for polar codes, then you can get even lower complexity compared to LDPC codes. But in terms of a practical implementation, it is actually not just the number of arithmetic operations, which is important. You need to take to look also at the decoding latency. And in terms of decoding latency, LTPC codes are very difficult to beat.
So when the number of iterations are a little bit small, I mean, for 5G codes, I think they use these layered type of decoders, which boost the performance a little bit. But when you are like limited to 20 or 8 or whatever, this is usually, I don't know, just as
yes, but actually for long 5G LDPC codes, you may need quite a lot of iterations. And if you reduce it, then you may have some performance degradation, even with the layered decoding.
Right. Thank you very much. Thanks again for a very nice talk.
Thank you.
Our next speaker will be Yuval Kasutov. Yuval is from Technion. Everybody knows Yuval. He's been doing a lot of very nice work on coding for data storage. I believe he won a Best Paper Award recently